Good evening, dear students and my dear parents for watching this program. Today's live session in physics for grade 12. You know, it's a live classroom. Otherwise we say it's the UAE's biggest classroom. My teacher, I once again welcome you all for this program. This is, as I mentioned at the beginning, it's a live program. If you have any queries or any doubts related to physics for those who are doing grade 12, you can right now call me, and if you want any doubts to be cleared, that also you can do that. But at the same time, for today's session, I would like to highlight some questions which are based on the board examinations. So the board based question papers we will see, especially those question papers which we had recently, that is 2015's question paper, board paper question, we are going to discuss today. So those who are doing physics in grade 12, so it would be better you can take your notebook, take your book for solving it, and in case if you have any confusions in between, you can straight away call the number displayed on the screen. Okay, and in fact, at the beginning, I'll give you a few pictures of one of the equations or few concepts related to one of the equations we have in optics. Okay, so based on that equation, most of you might have completed optics by now. So one equation there, and related to that there are a few questions. I'll first explain that, then we'll get back to the board questions. Right? Hope it is clear. So today's plan, today's class, we will have board based questions to discuss, but before that I'll just explain one equation and some questions based on that equation, which is treated as very important equation. So in optics, one of the equations we have seen is what you call as lens maker's formula. So lens maker's formula you must be knowing, and for various situations how the lens maker's formula is applicable and which all questions are they based on, which are the different types of questions based on this. Okay, you know the lens maker's formula, the basic format of the lens maker's formula is 1 by f is equal to n to 1 minus 1 into 1 by r1 minus 1 by r2. You see, this is the equation which we have as lens maker's formula. From this, what we can make out is this f stands for the focal length, r1 and r2 are the radii of curvature of the two surfaces, and lens has got two surfaces. N to 1 is the refractive index of the second medium with respect to that of the first. Okay, refractive index of second medium with respect to first. It means further you can write N2 1 as N2 divided by N1, where N2 is the refractive index of the second medium and N1 is that of the first medium. Okay, so now I'll give you, so this is the basic idea, that's a fundamental form of the equation. Now let's see if this equation is to be applied to a convex lens. You know, for a convex lens, you see the situation, both the surfaces are curved like this. This is one spherical surface, this is the second spherical surface, and if light rays are coming in this way, the first spherical surface, you know the radius of curvature r1, first or second spherical surface, how do you determine? We determine the first or second spherical surface depending upon on which surface the light is falling. Light is falling on this surface, therefore its radius of curvature is treated as r1, therefore the other one's radius of curvature is r2. So according to the convention of sign we are applying for in light, in optics, we have r1, r2. r1 is measured in the direction of the light rays. You know, according to sign convention, the all distances are required to be measured from the pole, or here what you call as optic center, and those distances which are measured in the direction of the light rays to be taken as negative, opposite that is positive. So we can further say R1 is therefore positive because it is in the direction of the light ray, and R2 is negative. So, how will this equation be then? 1 by f becomes equal to n to 1 minus 1 multiplied by 1 by R1. R1 is positive. See this equation, minus R2 is negative now, so minus minus, so it will become plus. You see, this is the equation we are going to use if the cases of the convex lens. So, for a convex lens, the equation is becoming like this. You see the difference? The fundamental form of the equation is 1 by R1 minus 1 by R2. If it is to be applied for convex lens, it should be this one, 1 by f is equal to into 1 minus 1 into 1 by R1 minus 1 by R2. It's clear. Now, what else is? Look, think of this quantity n to 1. Okay, so this quantity is refractive index of the second medium with respect to the first. Okay, usually when you keep lens in air, let us say, air is the medium, then the refractive index of glass, that is N2, obviously it would be greater than that of medium, that is air. N2 is normally greater than N1. But you see this, when N2 is greater than N1, what you can make out from this, N21 would be greater than 1, right, because numerator is greater than denominator usually. So, N21 is greater than 1. Now, look at this part, when N21 is greater than 1, what do you say about this? Okay, so this part, this is greater than 1, so this minus 1 is positive, correct. So, this part is positive. How about this part? This is anyway positive. So, positive into positive. So, focal length is positive. Focal length positive indicates what? The lenses, see this is convex lens, you know, convex lenses are usually converging lens. And you see when the light rays are converged to a point, this point, when the light rays are converging to a point, that focal length is called, that is the positive focal length. So, positive focal length refers to what? The case of converging lenses, right? Positive focal length is converging lenses. So, what do you make out? So, let us conclude this way. A convex lens is normally a converging lens because this part is positive, this is again positive. So, focal length is positive, it indicates the lens is converging. So, nature of a convex lens is converging. Is it clear? However, we take the exception here. You know, if suppose the lens is kept immersed in a medium of greater refractive index. So, there is a typical example, you know, the liquid called carbon disulfide CS2. In carbon disulfide liquid, what happens is, you know, its refractive index is nearly, you know, 1.6, which is above the refractive index of water, sorry, glass. Glass refractive index, that is that of the lens, the refractive index is 1.5, but carbon disulfide refractive index is 1.6. So, what you make out is, if you dip a lens inside carbon disulfide, if you are immersing a lens inside carbon disulfide, then what happens is medium has a greater refractive index. When medium has greater refractive index, see, N1 becomes bigger than N2. It comes the other way, that is N2 less, that is lens has a smaller refractive index. Then what will happen? This becomes less than 1. N2 1 minus 1 becomes less than 1. When that is less than 1, now we look at this part. When that is less than 1, this part becomes negative. When this is negative, this is negative, this is positive. So, positive into negative. So, the focal length becomes negative. What you can conclude from the statement that focal length is negative? Focal length negative means the lens is diverging lens. You see this lens, suppose, you know, we have a concave lens, let us say. Concave lenses are usually described as diverging lenses. Why? Because, or from that you can make out that this focal length is measured in this direction. So, focal length negative. So, that means negative focal length indicates this is negative focal length. So, negative focal length indicates the lens is diverging and positive focal length indicates lens is converging. So, let us conclude this way. A convex lens, normal situations, that is when the medium's refractive index is less than that of the glass, that is ordinary situations, the focal length behaves as a converging lens. That is why normally we say convex lens is a converging lens. But in the situation when the lens is kept immersed in a medium of greater refractive index than that of the lens, then what happens is the focal length turns to be negative. If the focal length is negative, the lens is said to be diverging lens. So, convex lens is a converging lens normally, but can become diverging if it is immersed in a medium of higher refractive index. I hope the thing is clear. Okay. So, same way, if you think of a concave lens, what will be the picture? For a concave lens, yes, for a concave lens, we may make it like this. For concave lens, the situation is that this is how the lens's radius of curvature is measured like this. See, light ray is in this way and radius of R1 is measured in this way, and R2 is measured the other way. So, what happens is here R1 is negative, whereas R2 is positive, R1 negative and R2 positive. So, what does that mean? When you put it in this equation, we can make out, so how will this equation be? I am putting R1 as negative, that is I am putting this as negative. How about that? That is positive, that means it will become minus 1 by R1 minus 1 by R2. This is anyway greater than 1 in normal situations, that is refractive index. Then this part becomes positive, positive and negative together will become, focal length becomes negative. That is, the lens becomes diverging lens. Okay, that is, a concave lens is normally a diverging lens. Concave lens is a diverging lens. Okay, but what if it is immersed in a medium of refractive index, higher refractive index? Then this becomes less than 1, so this becomes negative, negative into negative it becomes positive, then focal length becomes positive, that is, the lens behaves as a converging lens. So, a concave lens, even a concave lens can behave as a converging lens. Convex lens can behave as a diverging lens also, if the lens is kept immersed in a medium of higher refractive index. That is why when you are asked to write the nature of a lens, so in the exams, in numerical problems, sometimes you may have to calculate the focal length. After calculating the focal length, you also may have to write the nature of the lens. So, you calculate the focal length and the value of the focal length you are calculating is found to be positive. That means the lens, the nature of the lens, you do not write it as convex lens, you should write it as converging lens. The reason being, convex lens, that is what I explained now, convex lens may become diverging as well if the focal length is negative, otherwise if the refractive index of the medium in which the lens is kept is higher than that of the lens. So, let us conclude this way. Convex lenses normally converging, concave lenses normally diverging, but it will behave just the opposite way if they are placed immersed in a medium of higher refractive index. So, for example, see, if the question is, just look at this question. Normally, we will draw convex lens as converging lens like this, but say just imagine N2 is the refractance of the lens and N1 is the refractance of the medium. A light ray is coming like this, one more light ray. Okay, if it is coming in this way, and what else is, if the medium's refractive index is, so the question is, if N1 is greater than N2, medium's refractive index is higher than that of the lens, then you trace the path of the ray. That is the question, trace the path of the ray. Tracing the path of the ray means it would be like this, this light ray, see, medium's refractive index is higher. So, what happens is, the lens will no longer be a converging lens, it will become diverging. See, the ray will go like this. In what situation? If the lens is of low refractance of the lens is less than that of the medium. Okay, so this is the case of lens maker's formula, and one question related to that is, the relation between focal length and radius of curvature. In the case of mirrors, we have the equation radius of curvature R is equal to 2f, twice the focal length. R is 2f is the equation which we know, but that is applicable only for mirrors, not for lenses. Do not get confused about that. So, radius of curvature is equal to twice the focal length only for mirrors, because in mirror the process what is happening is reflection, only one medium is what is involved, whereas in lens that what happens is refraction, two media coming into that. Okay. So, the radius of curvature is the only factor on which the focal length of mirror depends. For a mirror, when you make a mirror, whether it is concave, you are making it as concave mirror or convex mirror, whatever it is, the focal length is fixed. As long as the radius of curvature is the same, focal length is fixed whichever the medium it is kept. whereas in lens it is not the situation. So related to that we have the question. The question is, we have an equiconvex lens. Okay, equiconvex lens means the two surfaces have the same radius of curvature. R1 and R2 we are taking the same, let it be R. And also it is given the refractive index of the lens with respect to the to air, otherwise absolute refractive index is 3/2. The question is, show that the radius of curvature of the lens is the same as its focal length. These two are equal, you have to prove that. So how we again use the equation 1 by f is equal to refractive index minus 1 into 1 by R1 plus 1 by R2. Why plus? Because the lens is convex lens. I told you at the beginning, lens convex means you have to use this equation. Okay, but again it is given, it's an equiconvex lens. So that means radius of curvature R1 and R2 both we can write as R. Also it is, lens is immersed, it is not in any medium, it is in air. That means this refractive index you can write as just refractiveness of the glass straight away. Okay, so we will write this as what, 3/2 minus 1 into 2 by R. Okay, you solve this and see 1/2 into 2 by R. So 1 by f is equal to 1 by R. Therefore, we can prove that R is equal to f. So we proved that the radius of curvature is twice the focal length. This is, sorry, radius of curvature is equal to the focal length. Radius is equal to focal length only if the refractiveness is 3/2 and the radii of curvature are equal. Then only we can say R is equal to f. This also cannot generalize. This is only in this situation we are proving it. Okay. Now one more question. You know the power of a lens is 1 by f. Okay, focal length is this one. F is focal length. You express focal length in meters, and the unit of power is diopter. You know this. Okay. Now the question is, you know about the sunglasses. Okay, sunglasses. They have curved surfaces. Sunglasses. Okay, even if they have curved surfaces, you know it has got zero power, no power. Okay, so the question is, why sunglasses have zero power even if they have curved surfaces? Okay, so I'm going to explain that. This is how 1 by f is equal to, again, refractive index of glass minus 1 into 1 by R1 minus 1 by R2 is the equation we have in general. For a sunglass, you know, we may draw sunglass like this. This is the sunglass, let's say. Okay, very thin. Okay, so the two surfaces of the sunglass, they have the same, exactly same radius of curvature. But you see the light rays are coming in this way. This radius of curvature is R, let's say. The other radius of curvature is also R. How about the sign? They both measured like this, that means they both are positive. So R and R both are positive. So we will write 1 by R minus 1 by R. Then what would be the picture? When 1 by R minus 1 by R, then this is 0, so 1 by f is 0. 1 by f is nothing but power now. That is, power of the lens is 0. This is how we prove that sunglasses, even if they have curved surfaces, it has got 0 power. But if you have seen this, okay. Now one more question I will tell you. Imagine again we have an equiconvex lens. Okay, that is a convex lens having the same radius of curvature. Okay, now it has got a focal length f. Fine. Then I am going to cut the convex lens into two pieces. Okay, longitudinally I am cutting. If it is cut like this, what will be its focal length? That is a question. Once again, a lens, an equiconvex lens of focal length as f is being cut into two equal halves longitudinally like this. Okay, then what would be its new focal length? Alright. So first of all, you can write this for this lens, you can write the equation as 1 by f is equal to refractiveness of glass minus 1 into 1 by r plus 1 by r, because they are of the same radius of curvature. So you may write it as ng minus 1 into 2 by r. So 1 by f is equal to this one. So you may write it as equation 1. Now the second thing, this lens. Okay, when you consider this lens, again use this equation 1 by f is equal to refractive index is not changing because medium is not changing. Refractiveness minus 1 into, look, this is 1 by r itself. Look, this surface is not changing. How about the other surface? This is a plane surface. Plane surface, what's the radius of curvature? Radius of curvature of the plane surface is infinity. Okay, it's a plane surface. So we will say plus 1 by infinity. You know what is 1 by infinity? It is 0. So we will write ng minus 1 into 1 by r plus 0. This is 1 by f. By the way, this focal length let be f dash. Okay, the previous focal length is f. Now you just need to do is you just divide. Okay, you just divide equation 1 by 2. Okay, 1 by 2 you just divide the equation. Okay, then what happens is this by this 1 by f by 1 by f dash, it becomes what? F dash by f is equal to 2. Okay, rest all will be cancelled. So what do we get here? F dash is equal to 2f. So when a lens is cut into two equal halves, when a lens is cut into two equal halves, each focal length will have, each lens will have, each half will have its focal length double that of the previous lens. So simply saying focal length is halved when the lens is cut like that. In that case, if the question is about power, focal length is doubled. Okay, once again focal length is doubled. Initially the focal length is f, now the focal length becomes 2f. So it is doubled. So once again focal length is doubled when it is cut into two equal halves. How about the power then? If the focal length is doubled, what will happen to power? Power will be halved, because focal length is, or power is a reciprocal of focal length. So when focal length doubles means power will be halved. So when the lens is cut into two pieces in that way, the power will be halved, focal length will be doubled. Okay. Before moving on to one more question, before moving on to the board paper questions, I have one more thing to tell you. Okay. That is, listen to the question. That is just the situation again. A lens. Okay. A lens has got a convex lens has got focal length 20 centimeters. Let's say. So 20 centimeters is the focal length of a convex lens. Okay. By the way, when you use the terms convex lens, there are different terms related to that. One is like convex lens, or biconvex lens, or double convex lens. Remember, all these three terms, that is convex lens, biconvex lens, double convex lens, all refer to the same thing, just a convex lens, one convex lens. Okay. But if it is equiconvex lens, it simply means in addition to being convex, it should have the same radius of curvature as well. That's what we have seen before. Okay. Now coming back to this, we have a convex lens having a focal length 20 centimeter when it is in air. What you have to find is if it is immersed in water. So let me write this as FA, focal length in air. If it is immersed in water, what will be its focal length? Same lens in air 20 centimeter. In water, what will be the focal length? You know what all data given? Refractance of glass is given to be 3 by 2. Refractance of water is given to be 4 by 3. Okay, see, these two are given. How? Again, we use the equation 1 by f is equal to refractive index minus 1. Refractive index, I am going to replace this with value. Alright, first anyway you will write like this, ng minus 1 into 1 by r1 plus 1 by r2. This you may write as equation 1. This is in air. Now, if it is in water, how the equation is? 1 by f is equal to w, f of water, is equal to refractive index. Now what you will write as the refractive index in water? We are now immersing the glass or the lens inside water. So the refractive index of glass with respect to water comes. So there is a chance of going wrong over here. Sometimes you may get confused here. Remember, it is not simply the refractance of water when it is immersed in water. It is not simply the refractance of water. It is the refractance of glass with respect to water. Okay. So ngw minus 1 into 1 by r1 plus 1 by r2. Fine. Now next what you should do is we are going to find out the focal length when it is immersed in water. We just divide one by the other. So equation number 1 by equation number 2. Equation number 1 by 2, what will you get? Fw by Fa, 1 by 2, okay, is equal to Ng minus 1 divided by Ngw minus 1. You see, this is how the equation. But now let us put the values. This is Ng minus 1, Ng is how much? 3 by 2 minus 1 divided by. What about NGW? NGW means refractance of glass with respect to water. NGW, that means Ng by NW, that is 3 by 2 by 4 by 3. Okay, so 3 by 2 by 4 by 3, that is, you will get 9 by 8. Okay, so the refractance of glass with respect to water is 9 by 8. You understand that, right? Okay, so that value you substitute here, 9 by 8 minus 1. Okay, so that is, it becomes 1 by 2 by 1 by 8. So it becomes 4. That is FW, that is focal length in water, is equal to FA into 4. You know, you were given focal length in air, which is 20 centimeter. That is 20 multiplied by 4, which is nothing but 80 centimeters. So what do you understand from this? When a lens is immersed in water, the focal length becomes 4 times the original. So initially the focal length was 20 centimeter. Now it becomes 80 centimeters. So this, what was the question? Once again, let me tell you the question. The question was, a lens has got a focal length 20 centimeters in air. What will be its focal length when it is immersed in water of refractive index 3 by 2? The value given over here, the refractance of glass is there, refractance of water also is there. Okay, so this is the concept, and the same numerical problem which you have discussed can be utilized to, or it can also be used to explain what happens to the focal length of a lens when it is immersed in water. If that is a question, what happens to focal length when it is immersed in water? What will be the question? That is, initially in air this is the refractance, but when immersed in water, the refractance becomes refractance of glass with respect to water. When refractance of glass with respect to water means the refractance decreases. Okay, so this refractance becomes less than this. So refractive index decreases means focal length increases. That way we can say, we don't need to calculate anything. Just say when it is in air it has a given focal length, but when it is immersed in water, the focal length becomes less, it is reduced. Okay, focal length is reduced. Since, sorry, the refractance is reduced. Okay, initially refractance of glass, and when medium, refractance of glass with respect to water, that is becoming less than. So when refractance becomes less, the focal length increases. As refractive index decreases, focal length increases. I hope it is clear. Okay, so now we will move on to some of the questions from board paper. See, I have a question paper of last year 2015. Many question papers are there of different regions. It is there in the website of CBSE, and one of the question papers I have it with me is of Ajmer region. Okay, those question papers, just we will go through those question papers, and difficult questions we will discuss now. Okay, have a look at the question paper. Okay, so this is the question paper. Okay, so we have, there are 5 sections, A, B, C, D, E. Okay, in the first section, 1 mark questions only. Define dielectric constant of a medium and what is its SI unit. That's the first question. Can you say what's the SI unit of dielectric constant? Dielectric constant, when you say it is, first question is define dielectric constant. What is its SI unit? Okay, listen, dielectric constant means it has got 2-3 definitions. In fact, you write any of one of the definitions. Dielectric constant, one is permittivity of air, permittivity of the medium to that of air. That's one definition. See, epsilon by epsilon r. Okay, we have another definition, K. K means dielectric constant itself. C by C0. Okay, so this definition is there. Also, we have a definition of dielectric constant, F0 by F. That is force in air divided by force in the medium. So all these are there. But anyway, write one of these definitions. Mostly this would be better, or even this also. The dielectric constant of a medium is defined as the ratio of the capacitance of the capacitor when the medium is the dielectric. Sorry, if the dielectric is kept as the medium, and to that of the same capacitor in free space, or when the medium is free space. Okay, so this ratio is dielectric constant. And what is the SI unit of dielectric constant? That is another thing. Dielectric constant is a ratio of two similar quantities, no? So it has no SI unit. See the question, what is its SI unit? Dielectric constant. You may get confused over there as well, right? Dielectric, what is its SI unit? Specifically it is given, no unit. Okay, dielectric constant has no unit. Anyway, after a short break, we will come back again with these questions. We will discuss the remaining questions after a short break. Okay, stay tuned, we will be back.